Oh, hi. I'd like to talk to you a few moments about some applications of gas problems. Before we even get started on that, let's talk about some gases. Many of the cars out on the road today have airbags, and of course all the new ones do. And pretty elaborate schemes, airbags in the front, airbags on the side, airbags coming from the back for passengers and such. It's becoming quite an industry. The airbag reaction is shown up here on the board. This reagent is known as sodium azide, and it's extremely toxic. Workplace has limitations on how much sodium azide could be present in the air, and it's a little white solid. It's contained inside of a little capsule in the engine compartment. What happens is, if a bumper's hit, and it's hit so far that the computer on board says, hey, this is going to be a bad accident, deploy the airbag, a spark is sent here, and this is what we call decomposition of sodium azide. It breaks up into sodium, which would be a problem if it was in the presence of water, but what we do is throw in another couple of chemicals in this mix to mop things up at the end, one of those just being potassium nitrate. So we make some sodium metal, which is not our concern for the airbag, but this produces an enormous volume of nitrogen gas. So airbag fills up with nitrogen gas upon impact. Of course, talking about gases, a gas that's so important to us would be the O2 molecule. Oxygen gas. We often use red for oxygen. This is a double bond that we'll talk about a little bit later, and oxygen likes to travel in pairs, the O2 molecule. We breathe in, we breathe out. When we breathe in some nitrogen. 78% of our atmosphere is nitrogen. 21% is oxygen. We typically break this bond, and hemoglobin, traveling throughout the blood circulatory system, carries oxygen molecules throughout your body, and oxygen's utilized. Muscles, nerves, sight, things talking. The O2 molecule, 32 grams per mole. Let's take a look at a little problem over here on this left board. It's a very good, useful example of PV equals nRT calculation. Up at the top here, I've posed this little problem, and it goes that the student has placed a mass of an unknown gas inside of a flask, measures the mass of the flask before and after, so it says, hey, I've got 3.23 grams of this unknown gas. It's a 10-liter flask, so think of it as being about 5 2-liter soda bottles put together. Room temperature is 298 Kelvin. When we look at Kelvin temperatures, don't be alarmed looking at this number going, it's large. Like an oven temperature, it's not. On the Kelvin scale, 298 is about room temperature. Student measures the pressure using a pressure gauge, just like he or she would for a bike tire or a car tire, measured to be about 1/4 of an atmosphere. And what is the gas? So PV equals nRT is used because we have a static problem, meaning we can describe a gas. Nobody's cooling the gas, nobody's heating the gas or pressurizing it. We have a gas. In this problem, we're going to use N as our unknown variable and solve for it because we're asked what is the gas, and the amount would be very, very helpful. The others are measurable. We measure the pressure, measure the volume, measure T, the temperature, and R is the constant. So I've arranged this PV equals nRT, solving for N by dividing both sides by RT, and I've plugged in some numbers here. This turns out to be, let's see here, 0.247 atmospheres times 10 liters divided by our constant times 298. Let me write this down to 3 significant figures. Come up with about 1/10 of a mole of unknown gas. Now, I went ahead and wrote down moles, but let's take a look at our units. Atmospheres cancel. Take a look at what else cancels. Our liters, top and bottom, cancel. Do our moles cancel? No. We only have one occurrence of moles. It's in the denominator of the denominator, so it comes up, and our kelvins cancel. So we are correct in using moles. Now, to identify an unknown gas, molar mass, the units there are grams per mole. Well, the student was very, very sophisticated at the beginning of this problem, knew to weigh out the mass of the gas, 3.23 grams. So we have our mass, 3.23 grams. And we've used PV equals nRT, our equation of state, to determine how many moles of gas are present. 0.101 moles. No units will cancel. We'll end up with grams per mole. And after the division, it looks like Rounding, I still come up with 32.0 grams per mole. It's possible that our gas is some other combination of elements, but unlikely. We have 16 grams per mole for one oxygen, 16 grams per mole for the other one, 32. So our unknown gas very well might be 32. If you'd like to do further analysis on this, you might go ahead and take the gas, bring a splint nearby, a splint like a lit match, and we're expecting it to go quickly because of the oxygen. We'd be careful and do a controlled experiment with this. A nice application of PV equals nRT.